test number 2, we've actually already discussed the geometric series test. And for this test, we just have to recognize that the common ratio must be between 1 and -1. When I talk about the n umbrella, I will have you guys start to try to rewrite your expression for the nth term so that it's something to the nth power. So here, if I were to rewrite that expression, the nth term expression, I would move the -1 inside as the base being taken to the nth power, or rewrite that as 1/10 to the nth power. And anything that is considered the base, that's part of the base, is your common ratio. And so long as that is between 1 and -1, we can make the conclusion that the series converges. And if they ask which test, you would say by geometric series test, or because the series is geometric. So converges by geometric series test. The other test that we're going to talk about is the integral test. And the integral test simply states that if f is continuous, so long as the function is continuous, then if I can prove that the integral of the general term converges, then I can prove that the series itself actually also converges. So integral of the nth term behaves the same way as the series. So that statement right there, I will summarize below here. The integral of the nth term behaves the same way as the series. Okay, one note to make is that it does not mean that it both converges to the same value. So if you do take the integral of the nth term and you so happen to get a finite value, that finite value does not represent the sum of the series. It just tells us that if the integral does exist and it does converge to a finite value, that the series itself also does, but it does not tell us what sum it converges to. So that's an important note to make. It simply tells us it does or does not converge. Some of the conditions that has to be true before we apply the integral test is that the function, or if we were to plot the series itself, it must fall above the x-axis. So f must be positive. It must be a positive function. And it must be continuous. So kind of a lot of conditions here. Must be continuous. And lastly, it must also be decreasing. Decreasing because we want to know that each term that we're adding in the series, that the partial sums will eventually converge to a particular value. So those three are conditions that must be true before we apply the integral test. So what would this look like? So here's the example, and we've actually already done the p-series, and I know we referred to it as our p-series without really understanding that the p-series is what the proof of it comes from the integral test. So we're going to go back and take a look at let's see how we would do a problem in which you first start off, so the series itself looks like it has a summation notation. You have the series starting at 2 going on to infinity of 1 over n ln of n. And let me enlarge this here. And so let's say we got an example like this, and the question was, does this converge or diverge? Okay, so we can so the integral test works well. If you can integrate it, then you can go ahead and do so. So the replacement that you're doing is that if you prefer to call it x instead of n, you're integrating, you're taking the nth term, so your nth term is here, and I'm just changing it to x so it looks a little bit more familiar for me, and then I'm going from 2 to infinity. I'm converting that series into an integral and then integrating. So this ends up being an improper integral. So I'm going to let b approach infinity. We've got infinite bounds. 2 to b of 1 over x ln of x. And as we try to integrate this, we notice that it is u substitution that would work here. So let u be equal to ln of x. And I forgot the dx here. We've got du is equal to 1 over x dx. So therefore, if I replace the 1 over x dx with du, I have that I'm really integrating the limit as b approaches infinity of from 2 to b of 1 over u. 1 over x dx is going to be replaced by du. So my antiderivative after all of this, and let's move this up here, we have ln of absolute value of u, and u happens to be ln of x, so ln of x also within this, the argument of the first ln, and we're going from 2 to b. There's a limit in front of here. So let's plug in b, and then plug in 2. Evaluate the limit. So always with improper integrals, integrate, then evaluate the limit. So as we evaluate the limit as b approaches infinity of the natural log function is infinity itself. So this is infinity. And then again, ln of infinity, limit as b approaches infinity is also infinity. So therefore, the integral is divergent, and we can also conclude that the series itself that we began with is also divergent. And that is by the integral test.